In continuation to the previous lecture, today we will start immobilization technique. This figure shows immobilization techniques. First is adsorption, second is covalent bonding, and third is entrapment. Immobilization technique should be noted that although the agar entrapment method described here has provided a useful example, it is not a particularly effective form of immobilization. The high temperature required to prevent the agar from setting may lead to thermal inactivation of the enzyme, and the agar gel itself is very porous and will allow the enzyme to leak out into the surrounding solution. There are in fact thousands of different techniques of immobilization, all of which are much more effective than our example. In general, these techniques can be classified as belonging. First is, as shown in figure, first is adsorption, second is covalent bonding, and third is entrapment. First is adsorption. The physical adsorption of an enzyme to a supporting matrix is the oldest method of immobilization. As early in 1960s, J.M. Nelson and Edward G. Griffin described the adsorption of yeast invertase on to activated charcoal and the subsequent use of this preparation for sucrose hydrolysis. Over the years, a variety of adsorbents have been used, including cellulose, Cefadex, polystyrene, kaolinite, collagen, alumina, silica gel, and glass. Such immobilization procedures are extremely easy to perform as the adsorbent and enzyme are simply stirred together for a time, typically minutes to hours. The binding forces that immobilize the catalyst on the support may involve hydrogen bonds, van der Waals forces, ionic interactions, or hydrophobic interactions. Such forces are generally weak in comparison with covalent bonds. For example, a hydrogen bond has an energy content of about 20 kJ per mole compared to 200 to 500 kJ per mole for a covalent bond. Thus, when using such methods, yields, that is the amount of enzyme bound per unit of adsorbent, are generally low. In addition, adsorption is generally easily reversed and can lead to desorption of the enzyme at a critical time. However, despite these limitations, such a method was used in the first commercial immobilized enzyme application, namely DEAE Cefadex immobilization 1 amino acid acylase in 1969. DEAE Cefadex is an ion exchange resin that consists of an inert dextrane particle activated by the addition of numerous diethyl amino ethyl groups. Particles of this material remain positively charged at pH ranges 6 to 8 and thus bind strongly to protein, which are generally negatively charged in this pH range. If the pH is kept constant, the enzyme and support will remain ionically linked. However, when over time the enzyme loses its activity through denaturation, the pH can be adjusted to a more acidic value. The old enzyme will be dissolved and the pH can then be readjusted back to pH 6 to 8 and a fresh batch of enzyme bound. Thus, the support matrix may be used many times, giving the process significant economic benefits. Clearly, DEAE Cefadex immobilization is only of value for enzymes that have a neutral to alkaline pH optimum. For enzyme that function best under acidic condition, CM Cefadex is more suitable. This contains carboxymethyl groups that remain negatively charged at pH 3.5 to 4.5. Proteins at this pH are generally positively charged and will thus ionically bind to the support. Desorption of the enzyme will occur when the pH is adjusted to a more alkaline value. Due to the simplicity and controllability of this immobilization procedure, combined with the economic benefits of reuse of the support, ion exchange materials are now widely used as the method of choice in many industrial settings. This figure shows properties of DEAE Sephadex and BACM Sephadex ion exchange resins.